All right. Thank you all for joining us here. This is our 5th of 5 talks this week on topics in forecasting and data science. We've had a great series so far with a wide range of speakers. They're all recorded and available on Metaculus on the discussion post referencing Metaculus talks. And so if you missed one, feel free to go back and watch it. But today I'm really excited to welcome Sean Taylor here to discuss causal forecasting. Sean, I'll let you take it over.
Yeah, thanks for the intro, and I really appreciate the opportunity to speak today. I hope to make it pretty interactive, so if folks want to chime in and ask questions, or or make comments, or tell me I'm wrong, I would love to hear that. I think the preface for all the things I'm going to talk about today are that I have been working in this area for a while, but I've never really been forced to sit down and articulate my thinking on it. So this is the first time that's happening, and so I expect this to not be like a totally polished presentation, but instead be like maybe an introduction of some ideas and the way that I think about working at the intersection of forecasting and causality. So just to kind of give you a little bit of background, this is like a typical resume slide, but I think that the interesting part of my experience here, there's some pieces to it that all kind of contribute to the way that I think about this. So I used to be a research assistant at the Federal Reserve Board. It's one of my first job after college. And there we were working on macro forecasting and forecasting the US economy under different scenarios. So we would sort of like hand these reports off to Alan Greenspan and show him like, here's what we think is going to happen to unemployment and inflation and GDP growth under different scenarios for the US economy. And there were lots of models and lots of economists that contributed to those kinds of forecasts. So I worked on that a really long time ago, and I never really made the connection until recently that it was like related to what I was doing. Macroeconomic forecasts were related to what I was doing in my day-to-day at my job at Lyft. And I went on and got a PhD, and I did my PhD working on experimentation and causal inference type ideas, but applied to social science. So I didn't work on forecasting very much there, but I did get interested in prediction markets at the time. So I was like building a prediction market of my own for research purposes, and got really interested in eliciting information from people. So like, how do you get like what's in their heads and get them to tell it to you so that you can use it to build better models? I did some work on that. And then I went to Facebook and worked there for a while. While I was at Facebook, I worked on a forecasting package called Profit with the PH. And that is a Python and R package that's pretty popular for time series forecasting right now. I'm steering people away from using it because I think there are better alternatives at this point. But I got very interested in forecasting at Facebook, and a lot of people have used tools that I built there. That's more on like the pure time series forecasting side. And then when I got to Lyft, I ended up sort of working on a problem for quite a long time of using forecasting to better manage marketplaces. And that's where I think a lot of the ideas for me really converged on like an approach to using forecasts to do better decision making. And in order to do that, if you're going to like make interventions, which you do at Lyft, which we had the ability to set prices and change driver incentives and coupons for riders, that we needed forecasts that could tell us different scenarios and under different actions that we could take. And so that's where I got really interested in kind of like weaving together these forecasting and causal modeling ideas. So I'm going to try to like present that from first principles. And then right now I'm chief scientist at a company called Motif Analytics. We're a startup, and our product is not revealed to the public yet, but I hope someday to talk about that. All right, so roughly this is kind of like the layout for the talk. Like, so first of all, I just want to make the point that if you're forecasting something, you're like bringing information to bear on. There's some information that you want and some information that you have, and you're using the information that you have to try to like make an estimate of the information that you want. And in statistics, the only real way that one variable can be informative about another is if they are associated in some way, or like other people can sometimes call this correlation. A correlated variable is one that is useful because it can help tell you information about a variable that you don't have, if you know that there's a correlation. So for instance, like height and weight are correlated. So if I know your height, I have a better chance of guessing your weight. And so like this is sort of like a really useful tool and the one that we all use when we're making estimates of anything in the world for values that we don't know. And then associations basically only come about in a formal sense from certain kinds of causal models. And so like there's a perspective on statistical modeling that like all models are causal models. It's just sort of we're not being careful enough about describing them as such. And so I'm going to try to like be a little bit more careful about how we describe an association between two variables and show you how we can derive that from first principles as a causal model. And all causal models are directed acyclic graphs. There's this sense in which like causes have to precede effects, and there can be no loops, so effects can't cause causes. And so because of that, they end up with these like there's a representation of a causal model, which is like a graph, and the graph can't have cycles. And so that's a very general model. It can handle a lot of different use cases. And it's very useful for like reasoning about what you're actually doing. And so we'll see some examples of that. And then my goal here is to just show you that when you apply this perspective to forecasting tasks, that it yields some insights into like what we're actually doing and like what we might do differently under different scenarios, and how we might use forecasts as a better tool for say like making some kind of optimization, or setting policy or making decisions about what you want to do. All right, so two variables that are associated. So if I were to make a plot of two variables, x and y, and they looked like they had a correlation, it wasn't just random noise on the plot, like a bivariate distribution with no association. If they had any sort of pattern in them, then they would have to, in some formal sense, arise from one of these four graphical situations. And so we have x and y. X is a variable, y is a variable, and then we have these edges between them. And the edges are directed. So in this case, we say like x causes y, and in the second scenario, y causes x. And so these are both very clear cases where you would see an association because it's causal. So like when x is higher or lower, y will be higher or lower, and that could happen mainly because one is causing the other. So these are the straightforward causal situations and ones that are pretty easy to reason about. The sort of like often countervailing hypothesis is that x and y are correlated because they share a similar cause. And so like the reason why these two variables are correlated is because there's some unobserved, U stands for unobserved. Usually it is unobserved, sometimes it's not. And they're correlated not because they cause each other, but because there's some third thing that causes both of them. This is by far the most common scenario in life. The two things are associated not because they cause each other, but because some third thing that's more more kind of fundamental is causing them. So in the height and weight example, it's not that your height causes your weight or your weight causes your height, but that there's like you have genetics and your genetics are determining both of those things, and that there's some latent thing that we can't observe. It's hard to measure, and so we always see is the association, but we don't see the root cause of the association. And then there's this fourth scenario that I really hate talking about because it's a little subtle, but x and y can be correlated in this setting where they both cause something, and then you condition on that thing. And I'll spend one slide explaining that, and then we'll throw it away because it's not really useful today. But I think it's fun to think about because it does come up a lot, but like it's not relevant to the forecasting side of things, in my opinion. Maybe we could come up with examples where it is, but I don't want to do that. So on scenario 4, here's what that looks like. Let's say this is a good example I found from this guy Gareth Griffith's Twitter thread. I was looking for examples. There's like tons of examples out there of this situation. But basically, like let's say you had Hollywood actors was your population of people that you were interested in studying. And we know that people that are more attractive tend to be able to become actors in Hollywood. And also acting talent would also contribute to your ability to act in Hollywood. So people in the world, attractiveness and acting talent are uncorrelated. That's this like scatter plot on the right, and there's no correlation between all the points. But if we draw this threshold here and say like people who are high enough on attractiveness and some combination of attractiveness and acting talent, we would see these blue dots only. And so if we were to condition on someone being a Hollywood actor, it would look like attractiveness and acting talent are negatively correlated. And so this is an example where like you're conditioning on something without really thinking about it. but you end up with this correlation, and it might suggest to you that like high acting talent causes low attractiveness, or that there's some unobserved thing that's causing these two things to be negatively correlated. But actually, it's just that you condition on something. This is called a collider, and it's this example, this situation is called collider bias. All right, so I'm just going to so just for completeness, that's scenario 4, but we're only going to talk about the first 3 scenarios. Okay, so now we're forecasting, and in forecasting, there's this notion of time, and so time is always going to be represented left to right on my slides, and so we have an arrow left to right, and we have now is always going to be this dashed line going vertically on the page. Now in forecasting, we know the information on the left side of the dashed line, and we don't know the information on the right side of the dashed line. So here are like 3 scenarios that we could have based on the DAGs that we showed you before. X causes Y, Y causes X, and U causes X and Y, and the U and the X are both on the left side of the dashed line. And in all cases, the Y is the thing that you're trying to forecast. The thing is that one of these scenarios we can actually rule out by like the rules of causality is that an effect cannot precede a cause. So we really only have to care about 2 of these scenarios. So there's the shared common cause scenario and the causal scenario. And so it's roughly like all of our work that we're going to spend today is in sort of like trying to think about when are we in the top scenario, when are we in the bottom scenario, and when does it matter that we're in the top versus the bottom scenario. And what would we do differently if we were in one versus the other? And that's kind of the important thing. And this is like a really fundamental problem in causal inferences in general. When you observe data, so like think about what do I observe as the analyst? Like when I see this thing, I see X, and I see XY pairs from the past, and I see like a new X, and I'm trying to make a forecast of Y in this new situation. That's the data that we typically observe. And the interesting thing about causal modeling is that what it says is that each one of these, the data set that you see could have been generated by one of these 2 stories, or maybe some combination of both of those stories. And that which story generated the data, which causal model is the reason why the data are associated, affects how you reason about it and how you might make predictions about the future. And so this is kind of like why this is important. I wouldn't try to teach you like some new way of modeling things if it didn't change the answer sometimes. If it gave you the same answer, it would be very boring. Okay, so we're going to go through a quick example. I know this was kind of topical last week. Maybe everyone's grown bored of it. This guy Dare is somebody I follow on Twitter. He made an interesting point, and like I'm always in this mode of like putting things into causal models in my head, so I did this. He said Stuart Butterfield announcing that he independently decided to leave Salesforce without knowing Bret Taylor also made the same decision is actually a worse look for Salesforce than if this was an exodus based on the co-CEO leaving. Okay, so Bret Taylor is the co-CEO of Salesforce, and he announced his departure from Salesforce around the same time as Stuart Butterfield. Stuart Butterfield was the CEO of Slack and joined Salesforce in a very senior role. They both decided to leave. And so like, I think like in some cases, people would have said, hey, like Bret Taylor, the co-CEO leaving was what caused Stuart Butterfield to leave. And then what Dare is saying is like, actually, we know now because Stuart Butterfield told us that Bret Taylor leaving is not the cause of him leaving because he said he didn't know. So that suggests that there's the other explanation for this is that there's some unobserved variable that has caused them both to leave. And this is the bad look, right? So he's saying there's a bad look. Well, what does a bad look really mean? It's probably something like maybe the company's not doing well, if there's something internally like unsavory going on. I don't want to speculate too much, but it's just like kind of a fun example. So now like we have a different causal graph than we did before, and it's based on the new information. So the information that we have learned about the world has allowed us to like make a better causal graph than the one we had before, and it might change the way that we think about interpreting the information that has been provided by the situation. Okay, so let's say we had this information, all 3 variables were observed, like these 2 people leaving, and we were making a forecast of Salesforce company performance for like next quarter. So we're like interested in for a stock analyst, and we want to know like are they going to have a good earnings call or something like that. So in some sense, the information that Stuart Butterfield revealed that he left without knowing that Bret Taylor was leaving sort of makes our assessment of this variable the Salesforce company conditions, like it updates that variable. It gives us like a path toward updating that. And it's because in a causal graph sense, we can trace a path from that variable to this variable via this unobserved variable. And under the other causal model, we could not trace that path. Stuart Butterfield leaving would be caused by Bret Taylor leaving only. And him leaving would not have provided any additional information beyond just Bret Taylor leaving. Maybe I can even show you what that would look like because I didn't draw this properly. But if we had this causal graph, Stuart Butterfield leaving would not provide information because it's redundant with Bret Taylor leaving. So the graph from here to here would have already been included that. But under this causal model, it does. And so this is kind of interesting, is like when you're trying to accumulate signals about a particular unobserved variable that you think is useful for forecasting, like which settings under which that variable were observed and how it was created, like matters for how you interpret the information. So we have these two kind of ways in which historical data can be useful for forecasting a future variable. One is that it's directly causal. One is that it shares a common cause and therefore gives us information about the common cause. So just kind of like review what that looks like. Sharing a cause looks like this. This is, I think, like in a lot of ways, when you're doing forecasting, this is the main way that you do it, because direct causes of the thing that you're trying to forecast are kind of uncommon because there's not that many. Usually, there's only a small number of things that have strong effects. So usually, we're trying to like assemble scraps of information that together contribute toward a shared understanding of something that we don't have good information about. So you can think about like maybe the X's here are, maybe the U is the true labor market conditions in the United States, like how many people are actually employed, and are they like, are their jobs high paying, and are they leaving their jobs, or are people being fired? All kinds of dynamics going on there. And the X's are like reports or like other kinds of scraps of information. Like we see different people survey different sets of people, or we have different sources of information, like maybe from like LinkedIn or other kinds of websites that are like collecting information, and they're each releasing some information, and it's really just being caused by the underlying labor market conditions. What we're trying to forecast is like what the unemployment rate will be in the next quarter. So this is kind of like a really common forecasting setup, is that that you're using the information that you have to kind of come up with a better estimate for something that's like latent or unobserved. In the direct causation scenario, which is different, we have a direct causal relationship between the variables. So when we observe the variable, we can directly update our forecast based on that information, because it directly affects it. And this is I would call this like a scenario-based forecast. And in this setting, there are actually two setups. One is that the cause has been observed, so it's on the left-hand side of the dashed line. Or one is that the cause has not been observed yet. It's on the right-hand side of the dashed line. If the cause is known in advance, then you can use your knowledge of causal effects to update your forecast in a correct way. So let's say like we know historically that when senior product people at companies leave, that the performance tends to go down. And we have a lot of historical evidence to say that. So the moment that we observe Stuart Butterfield is leaving Salesforce, we could go and like take our Salesforce company estimate and like go and drop it by the appropriate amount in order to update the forecast. On the other hand, if we had not known that information yet, that he was leaving, we might have like in our heads some variable there that's set to 0 that could be set to 1 at some point in the future. And then it's helpful in this case to make a scenario-based forecast where we have a forecast that differs under different settings. So like, let's say he leaves in one where he doesn't, and that this forecast would depend on that forecast in some way. And so we would have to kind of average those forecasts in a way that captures like that there are two scenarios that are possible, and that the forecast would be different in those two settings. Here's what this looks like in terms of a modeling standpoint. Is like what we really kind of want is this like function f, which is like, it says, hey, if the executive leaves a company, what happens to the firm performance? And so like, what are we doing when we're building this model, and what other information are we bringing to bear the forecast? We're taking like cause effect pairs from the past and kind of like averaging them into a model F, which is helping us like estimate like what happens in that scenario. So this is another way that historical information brings information to bear on a forecast in the causal model sense, is that I need to estimate this causal function. In some ways, you could think of this graph here as a function, where like this is the output of the function and this is the input to the function. And so we need to have access to that function in order to make these scenario-based forecasts and make a better version of them. And the way that we estimate that function is by like conditioning on a bunch of cause effect pairs from the past. So it's interesting to think about how we might think of like use this information in practice. So let's say we still have the same scenario. We have Stuart Butterfield's going to leave Slack within the next like whatever number of days, and we have like a forecast of that. And then we have a forecast of what revenue would look like for Salesforce under those two settings. And so we could just take those two things and average them and come up with a pooled forecast. And so this would be our forecast for Salesforce company performance overall. And it would depend on which of these two scenarios, but we have to average the two scenarios to get the full forecast. And so in some sense, we might do a better job of forecasting because we get to work within these two scenarios, which are sort of like where more knowns are known, or more unknowns are known, and then we're able to kind of like create better forecasts and then average them. And then if we did that task separately, we could actually use it to estimate what I'm calling a quote unquote effect, like an effect of Stuart Butterfield leaving, which would be like the yes scenario minus the no scenario, which is to say like, oh, it would like maybe decrease our forecast for the revenue for the company. On the other hand, we could work backward the other way. So we could say like we have this effect estimate from historical data, and I have this pooled estimate, and I could like use the effect to like tease apart what would happen in the yes and no scenario. So there's like a kind of reverse way of doing this, where like I know the effect and I know the pooled estimate, and I can go backward to producing this. And so each one of these strategies might be reasonable under different circumstances. And so it's sort of like worth thinking about like when you might be wanting to do one or the other. I think it's interesting in some cases, like if you have this and you can generate this, that can be quite valuable because it's interesting to know what the effect of something happening will be. But if you have an effect estimate, that's often the input to a forecast. And so that's sort of like the world that I tended to live in, is where we have some evidence about like what the effects should look like, and then use that to back out what the difference between the two scenarios would look like. Does anybody know why I put effect in quotes here instead of like just saying it's a causal effect? So in this graph here, if it's just these two variables, it is an effect. It's like directly interpretable as an effect, because I'm making the claim that the performance is directly affected only by Stuart Butterfield leaving, and there's no other edges between the two things. But it's confounded by company conditions in the way that we were previously worried about. So there's this like other explanation here that for the company performance, which is that it's the reason why he's leaving. And so we don't actually know if him leaving is due to performance or just some random thing. And so we would ideally have some experiment where we have executives like flip coins and decide whether to leave a company based on that basis only, and we could rule out the presence of this edge here, which is the thing that is causing them leaving. That's a confounder. In the case where we have this confounder present, we cannot really adjudicate between these two hypotheses, that it's the conditions that are going to cause the performance to be different, or it's the executive leaving that's going to cause the company to have lower performance. So the context matters in how we interpret this information. Like if we knew that this person was leaving for like personal reasons, random reasons, maybe they got like a health problem, or like they're leaving because they got an interesting offer to work on something else, or like there's a cause that is not the company conditions, then we could rule out the influence of the first edge, and we would get a different estimate for the effect of the executive leaving, because the historical data of executives leaving companies would tend to be generated by situations where both of these effects are in place, like both from the conditions and from the person causing the performance of the firm to go down. So we need to think about the context of like when we interpret information from the past, what causal graph was in play for the information that we were gathering. So if you were doing a study of like firm, executives leaving companies effects on firm performance, you would really need to take into account that the fact that they are leaving is endogenous in econometric terms. It's like it's caused by something that we don't observe that could potentially also be causing the outcome. So just a quick example of like where you might use this information. Let's say like, you know, I don't want to be too bleak here, but let's say there's a future pandemic that happens, and we have to estimate whether there will be high inflation after that pandemic. Now, we know in the 2020 pandemic that there was this economic stimulus package that was generated by the pandemic, and that is an alternative explanation for why there was high inflation. The other explanation was that because there was a pandemic, that we had all this supply chain problems, and supply chain problems are the cause of the high inflation. And so we don't really know from the 2020 situation which one of these two things is the direct cause of high inflation, or maybe it's a combination of both. So in this like future pandemic, we would really want to know if there is going to be an economic stimulus package, and if there weren't one, then the old data would not be relevant for forecasting this, because we would be worried that like this setting would not be in play. So whether your old data that you have collected is like valid for the situation that you're trying to forecast depends a lot on whether the same conditions hold in a causal sense. All right. So I just want to give a quick example of how these ideas play out in practice, and like how we use them at Lyft. So to a first approximation, the Lyft causal graph looks a little bit like this. So a day on a ride-sharing platform, basically there's a supply variable that we want to forecast, which is like how many drivers are we going to have show up and drive on the platform. We have a demand forecast, which is like how many people are going to look at the app and try to see if they want to take a ride. Then we have those two things combined supply and demand are going to determine like how many rides that the platform provides. But also price level is going to determine whether those people take rides. Because if we charge like an arbitrarily high price, very few of those sessions will turn into rides. So we have this like variable that like Lyft controls that determines the outcome. We also have the ability to affect the number of available drivers on the platform through giving them incentives. So Lyft can send extra money to drivers in order to incentivize them to drive more, and that creates more available drivers on the platform. And then price level also happens to affect future rider sessions, because when people observe high prices, they tend not to like use the service as much again in the future. So these two variables here, price level and driver incentive spend, are variables that Lyft controls. They're no longer scenarios. In a sense, they are scenarios, but they're also scenarios that Lyft can choose from. Lyft can choose among the scenarios for price level, and it can choose among the scenarios for driver incentive spend. And because it can choose from those things, it actually has some control over the system. And the causal forecast is now a tool that can be used for policymaking. This is very, very similar to like when I worked at the Federal Reserve Board. Why were we doing these scenario-based forecasts of the US economy? It was because the scenarios for under different interest rates, federal funds rates, were controlled by the Federal Reserve Board. So it could choose to change the federal funds rate in a way that made the forecast look the way that it wanted it to look. In order to do this game, you need to have causal models available. So just like we had before, like I need to know effective executives leaving firms. I need to have good evidence for like the causal effect of it versus the confounded effect of it. So at Lyft, there's sort of like two curves that are needed here, at least two, and probably also the pricing curve. But incentives will cause more drivers to appear on the platform. And also more drivers will produce more rides under different different like numbers of sessions. So we have this kind of like these two curves that have been estimated from historical evidence that we can use then to combine with the forecast for available drivers and the number of rider sessions, and then use that to optimize the number of rides taken, and maybe even make a trade-off for like how many rides sessions we're going to lose in the future if we set price levels high or low. So when we pool these forecasts together, we end up with like a kind of combination of like what I would call like coupled forecasts, like that they move together in lockstep according to this causal model of the world. So a Lyft would be like, hey, we know in the past that we had lowered prices a few days ago. And so because we lowered prices, we know that we're actually going to get a demand increase over the next few days. And in order to meet that demand increase, we're going to have to increase the available supply of drivers. And we can do that through changing our driver incentive spend variable. So we call this like a planning variable. This is a variable that we have control over, but we've made changes in the past that we need to account for. And so the causal model needs to take account for that in order to kind of ensure that we have the right estimate forecast for rider sessions. And then this is a goal variable. It's like we want a goal on hitting the right number of available drivers to maximize the number of rides that we're able to provide. So we built this at Lyft, actually, and we had a very kind of like very complete model of the whole marketplace, including a lot of different variables that I haven't discussed today. There's a coupon. I'll show you the blog post. You can read about this some more, but we have weather. Weather affects both supply and demand. There's a driver hours model, a pricing model, a conversion model, and a rides model. So there are all these models that kind of like link together the variables in a way that makes the forecast move in lockstep and allows us to explore different scenarios. Like if we change different variables, what would happen to the forecast, and they would all change in a way that made sense according to the causal model that we had created. So just to show you what this looks like in practice, the spend variable is a very interesting one because it's expensive for Lyft to spend money on driver incentives. So you'd be interested in sort of like these curves of like, once you have this model strung together, you can say like, if we move spend left and right, what will happen to driver hours? What will happen to our amount of prime time that we charge? What will happen to rides? And you can see that you always get more driver hours for more spend. You can always get more rides for more spend, but it gets progressively more expensive. These curves are like, having a point that's like the optimal point where you make the trade-offs appropriately. And you can do that based on a forecast. You can also wait until the data are in for the week and see if your forecast, your actual data that you've observed and the forecasted data are aligned, and like whether you have regret. Like, did you make the right decision now that you know the information about what actually played out in the marketplace? And so this is a game we could play, and we could use this to try to like drive down regret over time and try to make decisions that we didn't regret. So like try to make decisions where we tended to choose the spend for driver incentives that was aligned with like the best possible plan that we could have known at the time that we made the decision. All right, just to kind of recap, I know I'm a little over time here. So in some sense, forecasts and all models depend on sort of a causal model in a formal sense. So like where do variables come from? Where does data come from? It comes from like a world that is generated through causal relationships between things that are happening. And there's two main ways that this contributes to forecasting. One is that shared causes provide a lot of useful signals about variables that we're unable to observe. But the causes themselves and the observation of them are useful signals. And I'm sure you would see in the metaculus data that when things happen, that a lot of forecasts are updated very quickly because people realize that there's a causal relationship between those things happening and what should happen in the forecast. And if we think about the causal model, it might provide us like information about what we should be paying attention to in order to provide inputs to forecasts and when they should change. If you have causal models available to you, or you're willing to kind of write one down, you can do this scenario-based forecasting technique and try to like unbundle your forecast into different scenarios, and that can provide either like better forecast because you're able to do a particular forecast for each scenario, or because you have information about a causal effect from an earlier study that you've done. You can kind of reason about what would happen under different scenarios, and that can be the other way to answer the question. And finally, some of the scenarios are under control, or like policy questions that we have, or policy questions that we want to inform. And that in that case, if you're doing some kind of scenario-based forecasting, you can actually estimate using the forecast like what the effect of taking different actions would be, and that might provide better information about what we should do for all kinds of different policy questions in the future. So really powerful technique if you get it right. Lots of things that are hard about it, but it's a very powerful way to kind of like put things into a shared context where you can reason about lots of different things, and also you can be critical of like which scenario are we in and which causal model is the one at play, and it gives you different answers to the question, and you can see how sensitive your answers are to to how much you know about the world. Finally, if you want to learn more about all this stuff, I think we wrote 2 blog posts on the Lyft scenario, so called Causal Forecasting at Lyft. So if you search for that, you'll find 2 posts on Medium. They're quite good, written by people I used to work with. I also recommend the Book of Why, Judea Pearl, and a kind of more readable, more academic style book is Counterfactuals and Causal Inference from Morgan and Winship. But I don't know any current work on like causal forecasting per se. Like I'm sure people might know more than I do, but like I think if you learn the causal modeling side of things first and then learn forecasting together, you'll see that these ideas actually work quite well together, and that like all the stuff I'm teaching today sort of like is a very aligned and reasonable way of thinking about the problem. All right, that's all I have.
Thank you so much, Sean. We already have hands going up, so apologize if I pronounce your name wrong, but Christianas.
That's very good indeed. Yeah, Christianis is good. Hi, Sean. Thanks very much. Very clear and concise talk. Very interesting. The Lyft scenario in particular. So I have the following question. So, you already alluded to kind of, forecasting your action, the effects of your action. So like, setting a price and so on and so on. Now, in a scenario where you have a Lyft scenario, which might be more complicated than what you showed, but you have competition. So, if I'm choosing Lyft, I'm looking what the prices for Uber are, right? And then people might be doing that. Now, do you think that kind of, variable can be modeled in a causal graph as just a node or a multiple nodes with a function that, somehow responds to, to your actions? Or do you think that some sort of game theoretic, maybe, a mechanism would be needed, like assuming that Uber and Lyft are two agents that are basically doing the same kind of modeling and competing on the prices or something like that?
Right.
Which way would you go?
Yeah, it's a great question. And we talked about it quite a bit while working on the project. And in a lot of settings, I think you can always make a model more complicated by introducing more variables. I think that's kind of like a common tension. It's like when you're modeling things, what things should be in the model and what things shouldn't. So one of the things about competitive data is that it's very noisy and hard. It's hard to observe, right? So it kind of qualifies as an unobserved variable. So in some ways, it was like we can put it in the model, but we don't have measurements for it, so it doesn't really matter. Is number one. And so often we would sort of decide like, hey, we have to do a tractable version of this problem for now. And maybe later, someday, we'll add complexity to the model in a way that accounts for that better. I agree. Like most economists would say, hey, you have to solve for some equilibrium here, and like if you had all that data from Uber, you'd probably do that. But I think in practice we didn't, and so we just sort of did this. The other thing that's interesting is, so in our model, we do have historical price variation at Lyft. So they do run experiments where they change prices. And when they change prices, presumably Uber does in response to that. And so the causal effect that's measured from the historical Lyft experiments in some sense captures the competitive response because it's at least as long as Uber's competitive response is consistent with what it was in the past, that you're capturing that a little bit. So like if we raise prices and Uber does this well, then the effect of the price increase will be less than if Uber didn't. But when we do in the past, actually they do that. So the confound is consistent across time and in the forecast. So it's like okay. But I agree. It's sort of like easy to think about ways that your model could be wrong all the time, and you need to be vigilant about that in general. It's like, well, what are we missing here, and why would it change? Why would it change the model and the forecast and the implication? It's a really important part of this process.
Yeah, makes sense. Tractability is a good variable to look at. Thanks very much. Good answer.
Right, absolutely, yeah.
Anyone else with questions for Sean?
Anybody working on something like this? Be very curious to hear.
Yeah, Ryan.
Yeah, this is a super interesting talk. Thank you for this. We're working on some like forecasting kind of trying to figure out what policies may be causal, like for government advice kind of applications, policymaker advice. So yeah, this is all super relevant related to that, and yeah, trying to figure out how to tease out causality seems super difficult and complicated. And you're seeing your model from Lyft, so it looked pretty impressive, and I'm sure a lot of work went into that.
It did. Yeah, I appreciate that. I think that like it seems a little overwhelming and hard, but there's a process to this that's actually pretty tractable, which is to just gradually complexify your model over time. So you can start with like simple models that have just a couple of variables, and you can reason about what the main causal factors are and what evidence do you have to bring to bear on that relationship. Each one of the arrows in one of those models is kind of like a study that you'd like to have, right? Like, oh, what's the effect of X on Y? And what we did at Lyft was like, I literally made a list of every node and edge in the graph, and we made it like a to-do list, and we went. It took two or 3 years to do it. It was a lot of work, but there was a process that worked, and it wasn't like some big, genius idea. It was just like a gradual building of a model that we trusted more and more. And so I think like in some sense things like this can look like, oh, that would be impossible to build something like this, but I actually think like, you get a lot of the value out of the simpler version, and then you can kind of like layer, hey, like, well, what about like, Christianas's question about competition? What do we know about competition? Can we like add that? Can we test whether the model makes sense in these other kinds of scenarios? So as long as you have this like dialogue with your model where you're constantly improving it, you can kind of converge on a good solution. It doesn't have to be perfect.
Did you find that you had to like rearrange like your causal, where things fit into the causal plan quite a bit, or was it?
Yes. Yeah, it's it's a kind of setting where you don't want to be too attached to any particular model, right? Like models are just tools, and like if they're wrong or they don't do well, or you have challenges with tractability, like it's not, I don't have this variable, like then you can't do that, and you have to come up with a way that is tractable. So like the feasibility constraint, it's like it has to be feasible, it has to be data that we already have. And then you have to fill in the blanks, and you have to be very flexible about it. Which is why the blog posts that you'll read, if you do read them, talk a lot about building a modeling system, which is like not saying like we built a model, which is like the model, but building a system for building models and iterating on models is really the kind of key idea there. It's like, how do I iterate quickly between models? And I think the people who actually get this right, it's like when you work in a spreadsheet and Excel, and like we look like we're doing all this kind of fancy stuff, but like at the end of the day, the Lyft model is just like a very large, complicated spreadsheet that we built in code, and that you could make changes in a very easy modular way to it. And when people work in spreadsheets, I think they do this all the time. They generate like scenarios. You have different columns for scenario A, B, and C, and D, and like you can complexify it or add new scenarios. So we just did that in a kind of, I think, a little bit more rigorous way where we could backtest it, like run it over historical data really quickly, see if it worked well, stuff like that. But at the end of the day, the ideas are, I think, basically the same thing.
Awesome. Super interesting. Thank you.
My pleasure. We have some in the chat that I think are pretty interesting. Any good causation without correlation anecdotes from practice? This is like a really fascinating one to me, because I think like as a causal inference trained person, you're kind of constantly looking for situations where like, hey, the correlation isn't right, and the causal relationship's different than the correlation. And I think like in practice, it turns out that like the correlation and the causal relationship are correlated in a way that's pretty consistent. So if you see a strong correlation, often that suggests that there is a causal relationship. And so like, statisticians are always worried about bias, right? Like, oh, you overestimated the causal relationship between two things. And we sort of like know that there usually is a bias when there's correlation. But where there's smoke, there's fire, right? It's like usually it's uncommon to find cases where you see like a strong correlation, but it's not in like causal, at least like it's like a 0% of that correlation is driven by causality. I had an occasion to read the paper where they kind of like proved that smoking causes cancer. It's really worth reading. It's like, it was written in 1950. It's quite old. And they can't run an experiment where they like make people smoke, right? And so like there's no like experimental gold standard evidence for like smoking causes cancer. But the correlation was just so strong. And when you kind of account for all the other explanations for like why smoking is associated with carcinoma, that like you just end up with like really overwhelming evidence that like there's no explanations left. So I think the correlation is not causation is an easy straw man. Like I just throw it out like, oh, you're wrong because correlation is not causation. But I think it's actually usually a little bit more nuanced than that. So kind of just like a philosophy that I think folks should think about a little bit more.
The
Peter?
question was about causation without correlation, such
Causation.
as like when you have some kind of like weird feedbacks, and how does this all show up in practice? I know you can design a system that does this, but
I have never seen that before. Yeah, it's like it's one of those things that's like theoretically possible to observe that, but I've never seen it. I would bet Andrew Gilman's blog has a post about that. I bet someone's asked him that at some point. That would be my first place I would look. But yeah, I've never seen that scenario. Sorry to misread your question. Peter Lau says nonlinear relationships is one way to get zero correlation. Yeah, this is true. Like when I was talking about the difference between an association and a correlation, this kind of a precise language I'm trying to use there. So correlation is a way of computing a specific kind of association. Usually correlations are linear correlations, and in cases where you have nonlinear relationships, the linear correlation can be zero, but you can still have strong associations between things. So kind of like one of those, it's another one of these like statistical corner cases, but I'm trying to be correct about the language. Let's see, Peter says, on a given number of nodes, there are a lot of DAGs. How do you balance this combinatorial complexity with priors and effective sample size, or back of the envelope calculations to rule out problems like overfitting? Good question about like the number of possible DAGs is always quite large, and usually what you're trying to do is use your domain knowledge to simplify the set of possible DAGs that you consider. And you know, a lot of people who work in this space would basically say that the absence of an edge between two variables is the meaningful thing. Like you start with the completely connected DAG where like every variable is connected to all others, and you start removing variables is like one procedure that you could use. And effectively, there is a Bayesian interpretation of this, which is that like each one of those edges has a variable associated with it for like whether the edge should exist or not. And our priors are over the distribution for that parameter of like whether the edge exists. And when you believe the edge doesn't exist, it's like having a high mass on your prior at zero for that edge existing. But the edge could exist, so like you don't have like zero mass at like 1 where the edge does exist. And in some sense, all the edges are continuous variables, not 0, 1 variables. And so like it's really just like a strength of a relationship between two things. Andrew Gelman has a nice post also about saying like basically like causal graphs are a sparsifying idea, but like really every variable does affect every variable in the real world in some like really rigorous physical sense. So I think like on the overfitting side and like actually fitting the data, you know, like every model basically boils down to an evaluation problem. When you create a model, you should have a plan to say like, is this a good model or not? The hard part with causal models is that evaluation actually is quite challenging. Like, is this a good model is something that in the Lyft scenario, we spent a really long time working on, and it's very challenging to know if your model is any good, because you have to, if you make a change to the model, like make it more complicated in some way where you could experience overfitting, you have to go and evaluate it in a fair way. And forecasting is particularly hard to evaluate because you have to do these big back tests. You run out of data very quickly. In the causal modeling scenario, you only observe the outcomes from one of your scenarios. So some of your forecasts that you make that you're capable of making are not evaluatable. So you sometimes don't even know if you're good at forecasting like some of the scenarios, because some of the scenarios just like don't come up. I don't have a good answer to this. Like I just think that like, you know, what we ended up doing was coming up with a suite of evaluations for the model. Like it should produce reasonable answers to these questions. And there's this idea of like a held out experiment or held out counterfactual. It's like a good causal model isn't just good at predicting what will happen. It's good at predicting like what an experiment would estimate would happen between two possible options. And that's very hard evidence to gather. And it's why macroeconomics is a really challenging field, is that there just aren't like a lot of like, how do I validate that my Federal Reserve model that forecasts the US economy under different interest rate assumptions is any good? It's like kind of like a super hard question. And I don't think anybody really ever knows for sure if the models are very good or not. It's like a kind of preponderance of evidence situation. But you do have to worry about overfitting in general. And I think simpler models are attractive in the sense that you're like, it's like an Occam's razor thing. Like you're trying to come up with like the simplest model that can produce reasonable behavior so that you don't introduce a lot of complexity and stuff that could produce problems in the future. It's a cop-out answer, but the answer is it's just hard. Causation without mutual information is also interesting, but maybe too negative. Yeah, there's a lot of people in the weeds in the comments here. This stuff is very theoretically interesting, but in general, like the situations I've worked in is where the causality is very, you want to work in scenarios where causality is strong, right? Like if the causal relationship is relatively weak, you can treat it as second order. And the question is like often like what variables are first order to the situation that you're working in. So for Lyft, it's like prices are huge and driver availability is huge. And there are lots of other things that affect how the marketplace plays out, but we don't model them because like the relationships are too weak. So we don't like to get into these really niche scenarios where things are kind of like ambiguous. What do you recommend these days in place of profit? I full disclosure, I'm an advisor for a company called Nixla, and Nixla has been building a lot of great forecasting packages in Python. They have lots of different, they're building like a variety of them, and there's a whole suite of them. And I think that like in general, this is my favorite approach to forecasting these days, is to like kind of choose the right tool for the right forecasting job. Profit was a pretty opinionated model that fit like a certain kind of data generating process quite well, but for others, other data generating process doesn't work very well. Nixla has a suite of models, and so you can try them out and try to backtest them against one another and figure out which one works better for the scenario that you're in. And I think that that's where I'm gravitating these days for forecasting, is that like there's no one model to rule them all. And in fact, like people will try to sell you a lot of these like neural network based forecasts these days, and they are very, very accurate, but it's like a huge lift to fit them and very complicated. It takes a lot of time. And often like simple models of, you have a set of simple models and you choose the right or a particularly good version of the simple model that like usually that does quite well, and you don't need to worry so much about using the fancy black box thing that you're not really going to understand how it works. In my experience, forecasting also basically boils down to having good information, not having better models. So like the search for the best modeling package is a little bit misguided in my opinion. I think often it's like search for the best signals, and what can we use as the best information. And if you don't have a lot of information, then the kind of forecasts you want to make are often very simple, like moving averages and things like that. I will type the name of the company. It's called Nixla. All their packages are open source, so I'm not trying to sell you anything. I just think that they have a team of people working like full time on building forecasting packages. Profit is like still maintained by some volunteers. I don't personally work on it anymore, but it's a little understaffed. And I think like ultimately you want to use software that's made by a community of people that are actively working on the problem, rather than like something that's a little bit older that doesn't have as much support. All right.
Any final questions for Sean?
I really appreciate all the great questions so far, and the opportunity to share some like kind of unfinished thinking on the topic. And if any of this resonated with you, or you found it interesting, or you want to talk more about it, do feel free to email me about it. I'm really curious to hear like if you're using ideas like this, or you have challenges like this. Like I said, it's not an area I actively work on anymore. I have a new project that I'm involved in, but I do think it's really interesting and important work, and that like if you get this right, it can really make forecasts more useful and accurate for a lot of use cases that people have, and probably improve the world in a lot of ways. So hope they found this kind of like compelling.
Great. Thanks so much, Sean, for sharing with us all, and thank you everyone for attending. Have a great day.
Bye, everyone. Happy Friday.